Hello friends, welcome back to my channel. Today we are going to discuss about why different compounds have different colors. So you can see a series of metals over here. I want you to observe manganese, right? So manganese, you can see it is having its own color, somewhat like grayish kind of color. This is the color when manganese has lost 0 electrons. That means the oxidation state of manganese is 0. You can see over here that manganese is having an atomic number of 25 and its outermost shell is having an electronic configuration of 4s2 3d5. Here 4s2 3d5 with 5 unpaired electrons in manganese. So why I'm trying to tell you about manganese is because you can see over here that manganese is having different color. The same manganese is having different colors. +2, when it is +2, that means when it has lost 2 electrons, it's having an orangish color. When it has lost 6 electrons, it is having a green color. And when it has lost 7 electrons, it is having a violet or a purple color that's present in KMnO4. Okay, so this is KMnO4, K2MnO4, or you can call this as MnSO4, right? All these are having different colors. Now it is the same manganese, right? But why is it having different colors? Now you must be wondering what's the answer. So the answer is the answer lies in the number of unpaired electrons in the outermost shell. Now have a look at this. So the number of electrons in the outermost shell of manganese are like 25 is the atomic number, 4s2 3d5 is the electronic configuration, right? Outermost shell electronic configuration, 2 electrons. So when manganese had lost, that means the manganese oxidation state was 0, it was in the elemental state. That time it was having 7 electrons total in its outermost shell with 5 unpaired electrons. When manganese lost 2 electrons, that is +2, right? It lost 2 electrons, that is +2. It became 4s0 and 3d5, and 4s0 3d5 will look something like this. So when it is having 5 unpaired electrons in the outermost shell, it was giving us, with the +2 oxidation state, it was giving us an orange, a light orange color. And with that same manganese further lost electrons, like it became +6 meaning it lost a total of 6 electrons. Yeah, here 4s0, that means I'll have to show 0 over here, I'm sorry, 4s0. yeah, and for Mn6, that means it will lose all electrons, 4s0, all electrons except for 1. So we'll have just 3d1 left over here. That means it will look something like this, 4s0 and 3d1. It has lost a total of 6 electrons. And in case of manganese 7+, you must have guessed it by now that it will have 0 electrons in the outermost shell. That means there will be no electrons in S, nor will there be electrons in D. These orbitals will only disappear because there are no electrons present in them. Okay, so Mn7+ is the was giving purple color, and Mn6+ was giving us green color. So let us see why Mn is changing color. You can understand the change in color is because of the change in the number of electrons. The change in color is because of the change in the number of electrons over here. So electrons are responsible, right? Unpaired electrons, especially present in the d orbital, are responsible for color because these electrons, they absorb a certain wavelength of light and they emit a certain wavelength of light. Okay, now say for example, this is orange in color, this is yellow in color, this is green in color. Now why is it, actually this is my solid state model, but why this is orange, yellow or green in color? It is because the orange one, like if you write Vibgyor, we all know that, right? If you write Vibgyor, violet, indigo, blue, green, yellow, orange, red, okay, then apart from orange, it is absorbing all wavelengths of light, like from 400 nanometer, 400, 500, 600, all wavelengths it is absorbing except for the orange wavelength, and 800 nanometer red, that's also it is absorbing, but it is only reflecting out orange, and that's why this is appearing orange to you. Okay, and similarly, like if this is green, so it will absorb all the other wavelengths except for green. It will reflect green, it will give out green. The electrons are placed in such a way, the number of electrons are placed in such a way that they are absorbing all other wavelengths, they are giving out green, and that's the reason why it is showing that color. So any substance, if it is having a particular color, it is because of the number of electrons present in its outermost shell. I hope you got that. On the basis of what we have learned, we are having a question over here. We need to match the color of these compounds. So here we are having, say for example, copper nitrate. Copper nitrate will be blue in color. So where's blue? Here's blue. Then iron to sulfate. Iron to sulfate will be green in color. It's also called as green vitriol. That's why it's green in color. Oil of vitriol, that's H2SO4. White vitriol, calcium sulfate. And blue vitriol is copper sulfate. Well, magnesium chloride, it will be white in color. Cobalt chloride, it is blue when hydrated and pink when dehydrated. Okay, then iron 3 chloride, reddish brown in color. Potassium dichromate, orange in color. Then copper 2 oxide, black in color. So this is how we can get the compounds, and we can have different colors of those compounds based on the number of electrons present in the outermost shell. Okay, so then moving on to a few questions. Yeah, we'll complete these reactions. Come on, tell me. Zinc plus sodium hydroxide, Zn plus NaOH. What will it give you? It will give you sodium zincate, Na2ZnO2. Na2ZnO2 plus H2. That's what you will get. Then we want sodium aluminate. So we'll write aluminium plus NaOH plus H2O is going to give us NaAlO2. NaLO2 plus H2 hydrogen. I've not balanced it, but still you'll be able to understand. And I have another video in which I have shown how practically with the burner, with the test tube, and with the compound, actual compound, we have heated it and we've seen what color changes take place. So I'll drop that link of that video in the description. Please go through that as well. Then